we will next cover a couple of basic statistical concepts that are related to data. So descriptive statistics are some things, some numbers that we calculate from our data. They are like summaries of our data. To understand these basic concepts is important because quite often our more complicated models try to explain differences in mean or try to explain variation, assume something about the variance and so on. So to understand what these more complicated things do, we have to understand the basics. And this is partly high school mathematics, but it's useful to revise it now before we go into more complicated things. The first important thing to know is the central tendency, the concept of central tendency and dispersion. So these are data about 3,171 working age males from the United States, and we have data on their heights. And this shows the distribution of the heights. So we have some people that are very short, we have some people that are very tall, and most people fall into these bins somewhere in the middle. So each bar here presents a group of people, how many people fall into the category of, for example, 170 to 175 centimeters of height. So the bar presents the amount of people, and this is a histogram. It presents how these heights are distributed. Then we have the kernel density plot of the same data. So kernel density plot shows us the distribution in another way. So we just have a line, and this is the probability density function. That's what it's called formally. And the height here tells what is the relative probability of observing a person here versus a person here, for example. The area under the curve is always 1. So if this is the scale here is in the tens, then the scale here must be in the 0.0 something. So that shows us that most people are on the middle, and then there are a few small short people and a few tall people. Now the concepts of central tendency tells us where this distribution is located at. So are the people roughly distributed around 175 centimeters, or are they perhaps about 160 centimeters or 180 centimeters? So it depends. It tells us what is the location. That's another commonly used term for this where this distribution is actually at on the axis. We have two measures of central tendency that are the most important. The mean is the most commonly used. So mean is just the average. You take a sum of all these people's heights and you divide them by the number of people. Then if you have median, which is the height of a typical person. The median is calculated by putting these people in a line so that the shortest person is in front and then the tallest person is in the back, and everyone there is ordered based on their height, and then you take the person who is right in the middle. So it's the midmost observations value, and median is a useful statistic for quantifying what is a typical person like in the population, because it's not sensitive to some people that will be very tall or very short. For example, if we had a person here that was 1 million centimeters tall, which of course is impossible, then the mean would be affected, but the median wouldn't. So mean and median tells us what is the typical person or the typical company or whatever you're studying like. The other important concept is dispersion. So dispersion tells us how wide this distribution is. So is everyone about the same size, or is everyone between 174 and 176 centimeters? Or are people between 150 centimeters and 2 meters? So dispersion tells how widely these persons are separated. The most common or the used measure of dispersion is standard deviation. I'm not going to present you the definition, but it's important to know that one standard deviation is about plus or minus 1 standard deviation cover about 2/3 of the data. Then plus or minus 2 standard deviations cover about 95% of the data. So these green lines show the 2 standard deviations, and then 95% of the people about fit into this area. So standard deviation can be, if standard deviation was larger, here it's about 7.4 centimeters. If it was 10 centimeters, it would mean that these 2 standard deviations would be about a bit less than 2 meters, and this plus minus 2 standard deviation would be a bit more than 150 centimeters. So it will tell us that people's heights vary more. So standard deviation tells how much the observations vary. There is this joke about why standard deviation is important. There are 2 statisticians, and one is 150 centimeters tall, one is 160 centimeters tall, and they are crossing a river that has a mean depth of 120 centimeters, and they're debating on why should they cross or not. They decide not to because the mean doesn't tell what is the deepest part. So we have to understand also how much the depth of the river varies, instead of just knowing what is the average depth of the river. So standard deviation tells us how much variation there is in the observations. Then there's the concept of standardization that is also important. Standardization can be useful and it can be harmful depending on the context. But it's important to understand why we standardize and when. For example, correlation, which I have mentioned before, is a standardized measure, so it applies standardization. The idea of standardization is that you take the observations, they are distributed like that, and the mean is at 175 about, and standard deviation about 7 centimeters. You subtract the mean from every observation and you divide by the standard deviation, and that gives you a new variable that has a mean of 0 and standard deviation of exactly 1. So we are basically throwing away the data about the location and dispersion, and we are just retaining the data on where each individual is located related to other individuals, and we also retain the overall shape of the distribution. This can sometimes make things easier to interpret. For example, if I say that I'm 176 centimeters tall, it may tell you something about my height if you know what the average height of population is. If I would say that my height is at the mean, then everyone understands that typical Finnish males are about 50% of the time they're taller than the mean and 50% of the time they're shorter than the mean. So I'm average height. So standardization can make things easier to interpret, but it can also make things harder to interpret depending on the context. So standardization destroys information by eliminating the information about the central tendency or the location and the dispersion from the data. Then there's also variance, which is another measure of dispersion. And variance is related to standard deviation. It's used because it's more convenient for some computations, and sometimes variance is easier to interpret. For example, in regression analysis, we assess how much of the variance the model explains of the dependent variable. We don't do that in standard deviation metric, we do it in the variance metric. So the standard deviation has same unit as the original variable. So if standard deviation is 7, then we know that these bars are 7 centimeters from the mean. And if we multiply this variance variable by 2, then standard deviation doubles. So that's convenient. Then variance measures the same thing. It measures dispersion as well, but on a different metric. And variance is defined as the mean of square differences from the mean. So we take each observation, we subtract the mean, and we take a square or raised to the second power. And then we take a mean of those squares. That gives us the variance. Variance and standard deviations are related so that the standard deviation of the data is the square root of the variance, and variance is the square of the standard deviation. We work with either, typically if we just want to interpret how a variable is, distributed. We look at the standard deviation because it's in a metric that is easier to understand. So standard deviation is 7 centimeters. We can immediately say that the people are 60% or something of the people are between 170 and 185. So that's how standard deviations are interpreted. Variance is 54.79. So that doesn't really tell us where people are located at. But variance is useful for some other purposes, and particularly in more complicated models, we use variances. Sometimes you report both, so that's possible as well. The variance, the concept of variance is important to understand the concept of covariance. So the idea of that the variance was the mean of differences of each observation from the mean observation to the second power. So it's the same as difference from the mean multiplied by difference from the mean. Then we have another statistic called covariance. So here we have data on height and weight. The covariance tells us how strongly person's height is related to the person's weight. So we can see here that those people who tend to be who are taller tend to also be heavier. So there's a covariance here. The covariance measures how much two variables vary together, and it's defined similarly to variance, except that you don't multiply one variable with itself. Instead, you multiply one variable with another and you take a mean of that. Then the concept of correlation, which many of you probably know, is just the covariance between standardized variables, and correlation varies between -1 and +1. So correlation is a measure of standardized measure of linear association. When correlation is 1, then you know that two things are perfectly related. When it's -1, you know that two things are perfectly negatively related. When it's 0, then they are linearly unrelated. So correlation is a measure of linear association. That means that it measures how strongly observations are clustered in line. So this is a scatter plot of two observations, and one is a line. 0.8 is the observations are very closely clustered on the line. Then 0.4 is something that we observe with the plain eye. 0 means that there is no linear relationship, and then negative correlations means that when one variable increases, then another one decreases. So that's the same, except the direction is opposite. The correlation doesn't tell us what is the magnitude of the change. So we can say that this is a correlation of 1. There is a huge effect of the x variable on the y variable. This is a correlation of 1 as well. There is a small effect of x variable on the y variable. So the y variable here doesn't increase as strongly with the x variable as here. So correlation doesn't tell us about the magnitude of the effect. It just tells us how strong the association is. And this is 0 correlation because y variable doesn't vary. And then we have the negative correlations here. Importantly, correlation is a measure of linear association. So here we have two variables that are clearly associated. So there's a clear pattern, but it's non-linear. Here is another pattern that's non-linear, and this is a weak positive correlation, and this is a clear association, but it's non-linear. So correlation only tells us if we can describe the data with a line. There could be some other kind of relationship as well. So saying that two variables are uncorrelated doesn't mean that they are not related statistically. It just means that the relationship cannot be expressed as a line.